Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into one of the oldest and strangest questions humanity has ever asked. What is reality really? But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe, only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each in our own little slice of time. Now feel free to dim the lights, maybe turn on a fan for a soft background hum, and let's gently begin our journey into reality together. And if your mind begins to wander, that's perfectly fine. Let it drift. We'll still be here, quietly unfolding the story. So, what is reality? At first glance, it feels like the simplest question in the world. You look around, you see the room, the walls, the bed or couch beneath you. The weight of your body pressing down, the soft sound of your breath filling the air. Surely that's reality, the solid things, the immediate sensations. But if you take a curious step closer, you realize that what feels solid, what looks stable, may not be what it seems. Reality, once you begin to peel it apart, slips away like layers of an onion. The deeper you go, the stranger it becomes. Let's start with something familiar, an apple. You can imagine one in your hand, bright and red, or green and tart, or maybe the sweet golden kind you slice into a pie. When you hold it, it feels perfectly real. You can bite it, taste the crisp sweetness, feel the juice run down your chin. Nothing seems more solid, more certain. But imagine cutting into it, slicing deeper. You reach the pale flesh, then the seeds, and then smaller structures still. You zoom inward with your mind's eye, as if the apple were a map and you were travelling into its hidden landscape. At first, you find cells, tiny compartments like rooms in a vast city. Each cell with its walls, its little engines and storage depots. Then deeper still, inside those cells, you find molecules, chains of sugars and proteins, folded and twisted in complicated patterns. You might think that's as far as it goes, but no. Slice further, and molecules give way to atoms, the supposed indivisible bricks of the world. Atoms, it turns out, are not solid beads at all. They're mostly empty. Imagine standing in a cathedral, high vaulted ceilings, echoing emptiness, and in the very centre, a single speck of dust. That speck is the nucleus, and the great emptiness around it is the atom itself. Your apple, your chair, even your own body are all built from vast cathedrals of emptiness. But the nucleus itself hides even smaller mysteries. It contains protons and neutrons, each of which is stitched together from quarks, bound by gluons in a dance so tight that we've never glimpsed a quark wandering free. And some physicists whisper that even quarks might not be the final word. Beneath them may lie vibrating strings of energy, unimaginably small, playing the music of reality itself. Or perhaps space and time are not continuous fabrics at all, but woven from tiny discrete threads, like pixels on a cosmic screen. Other visions suggest that reality itself could be a hologram, the three-dimensional world around us a projection from a distant two-dimensional surface. And some go further still, proposing that at its deepest root, reality is not matter or energy but pure mathematics, numbers, patterns, equations existing timelessly and giving rise to everything we see. Already the apple feels less like a piece of fruit and more like a doorway. What seemed solid turns slippery. What seemed obvious turns strange. And perhaps you notice too that the act of cutting deeper never seems to end. Each layer reveals another. Each answer is also a question. But here's the gentle twist. This slipperiness isn't just in the apple, it's in your own experience too. Because the redness of the apple, the sound of your teeth crunching into it, even the very sense of solidity in your hand. Those are not properties of the apple alone. They are partly built inside your mind. Your eyes detect light, but the colour red exists only when your brain interprets that wavelength. Your ears detect vibrations, but the crunch becomes sound only in the theatre of your mind, and your hand pressing the apple feels resistance, but that resistance comes from electric fields repelling one another, not from any solid surface. What you experience as real is both the apple and your brain's translation of it. So, what is reality really? Is it the apple itself, the invisible cathedral of atoms and quarks? Is it the taste, the colour, the sound, all conjured by your brain? Or is it something even stranger, patterns of mathematics, or information in some cosmic simulation? These questions may sound impossibly abstract, but notice how they begin in something as ordinary as a bite of fruit. Reality is both the simplest thing and the most elusive mystery. It is what you hold in your hand, and it is what slips away the moment you try to define it. As we begin tonight's exploration, I invite you to hold this image of the apple with you. A familiar, everyday object, both comforting and ordinary, and at the same time a portal to the deepest puzzles of existence. We'll travel slowly from the world of senses to the world of atoms and fields, to space, time, and consciousness itself, but always gently, never in a hurry, like peeling an apple slice by slice, each layer softening into the next. For now, take a slow breath and feel the mattress or couch beneath you. Notice the gravity holding you close. In a moment, we'll begin our descent into the many layers of reality. But remember, however strange those layers become, the apple is still there. Its taste, its weight, its presence. A reminder that whatever else reality may be, it is also the quiet, ordinary world you live in each day. So we've begun with the apple, an object so familiar it feels beyond questioning, and yet inside it we discovered vast empty cathedrals of atoms, quarks bound by invisible forces, and perhaps even threads of mathematics humming beneath it all. But before we go further down into the strange depths of matter, let's pause. Let's step sideways into a different kind of question. Not, what is the apple made of? But rather, how do you even know the apple is red or crisp or sweet? Because in a quiet and slightly unsettling way, your brain is the stage on which reality is performed. When you look at that apple, what exactly are you seeing? You might say, I see red, but the apple itself does not contain redness in any intrinsic sense. The skin of the apple reflects light at certain wavelengths, around 700 nanometers for that deep red hue. That light enters your eyes, hits the tiny cone cells in your retina, and sparks electrical signals. And then, after a journey through tangled neural circuits, your brain produces the sensation you call red. The colour isn't out there, painted on the apple like ink on paper. It is in here, conjured in your mind. This becomes clearer when you look across species. Birds, for example, have 4 types of cones in their eyes instead of 3, which means their spectrum of colours is far richer than ours. What looks like a plain brown feather to us may blaze with ultraviolet patterns to them. A mantis shrimp has up to 16 different kinds of photoreceptors. To them, reality is bursting with colours we literally cannot imagine. The redness of the apple is part of your reality, not theirs. And if all of us vanished, leaving apples behind, there would still be wavelengths of light bouncing off their skin, but there would be no red, no colour, unless there were a mind to interpret it. The same is true for sound. Imagine you drop the apple on the floor. You hear a thud, a dull, rounded sound. But what actually happened? Air molecules were disturbed, rippled outward in waves. That's all, just pressure variations. It is only when those vibrations reach your ear, turn into electrical impulses, and finally ripple through the auditory cortex of your brain that they become sound. Without ears, without a brain, there is no sound, only silent waves in the air. This might feel strange, even disappointing, as though reality were somehow less than you thought. But perhaps it is more accurate to say reality is richer, because what your brain does is take simple signals, photons of light, vibrations of air, molecules drifting into your nose, and weave them into a theatre. A virtual reality headset you were born wearing, one that you can never take off. Every sight, every sound, every taste is part of that immersive show. Philosophers have long puzzled over this. Is there a real apple beyond perception, or is the apple only what your mind creates? A scientist named Donald Hoffman once described our perception as being like the icons on a computer desktop. You see a neat little picture of a folder, but behind it are millions of lines of code you never have to touch. The icon is not the code. It is a simplified interface designed to help you survive and act. In the same way, your perception of colour, sound, taste and touch is not the full reality of photons, atoms and fields. It is the interface that evolution gave you so you could eat the apple, not calculate its quantum wave function. This means that, in a quiet way, every creature lives in its own bubble of reality. Your dog, smelling scents 1,000 times more vividly than you, inhabits a world of odours. A bat sending out ultrasonic chirps navigates a reality shaped by echoes you cannot hear. Each species has its own desktop, its own user interface. Reality may be one thing at its root, but it is experienced as many worlds. Think about music. When you put on headphones, you don't hear vibrating speakers or shifting magnets. You hear a melody, something flowing, meaningful, even emotional. Yet if you stripped it down, it's just air vibrating at different frequencies. The music exists not in the air, but in the way your brain interprets those frequencies. The same is true for language. Right now, as you listen, vibrations are leaving my voice, but what you're experiencing is not just sound, it is meaning, a story, reality transformed into sense, and still perception isn't perfect. Have you ever seen an optical illusion where two lines of the same length look different, or a colour changes depending on its background? Your brain is not a neutral camera. It edits, guesses, and sometimes fills in the blanks. There's a blind spot in your vision, where the optic nerve leaves the eye, and yet you never notice it. Your brain paints over it seamlessly. So in a very real way, the world you experience is part raw data, part clever improvisation. Now pause for a moment and imagine this. You're holding the apple again. You see red, you feel its weight, you smell its sweetness. But in reality, there is no red without your brain, no smell without your nose, no solidness without the electrical resistance between your hand and the apple's electrons. So is the apple real, or is it an illusion? Maybe it's both. An illusion that is reliable enough to keep you alive. A theatre production that never closes. And if our senses are just this kind of interface, then what lies beneath? If we could peel away the icons, what code would we find underneath? Physics, with its equations of space-time and quantum fields, is one attempt to look past the desktop. But even physics, too, is a language. Another way of describing reality, still filtered through human thought. So we find ourselves balanced between two truths. On one hand, reality feels solid, immediate, and undeniable. On the other, what we actually experience is a construction, a virtual scene stitched together by the brain. And maybe that's why the question, what is reality, is so slippery. Because reality is not only out there, but also in here. It is the apple, and it is your mind tasting the apple. It is the photons bouncing, and the red you see. It is the air vibrating, and the crunch you hear. As we drift forward in this journey, keep this in mind. The theatre of perception is not a weakness, but a gift. It simplifies, beautifies, and makes life livable. If you had to experience every molecule, every field equation, every bit of raw data, you would be overwhelmed. Instead, you live in a simplified bubble, a dreamlike projection, and that dream is what we call reality. If perception already bends reality, you might wonder, what about time itself? Surely the passing of time is one thing we can all agree on. The seconds on your clock, the slow rhythm of your breath, the feeling of today giving way to tomorrow. But in the early 20th century, Albert Einstein showed us that even time is not what we thought. And once you hear his story, the idea of a single, universal now begins to dissolve like mist in sunlight. Picture yourself standing on a train platform. A train rushes by, its cars rattling and glinting in the evening sun. On the roof of the train, lightning strikes in two places, one at the front, one at the back. To you, standing still, the flashes look simultaneous, but to someone riding inside the train, moving with it, the flash at the front reaches them a split second later than the one at the back. For that passenger, the events are not simultaneous. Two observers, both correct, yet their now is not the same. This was Einstein's radical leap. The speed of light is constant for everyone, no matter how fast they move. To preserve that truth, reality must bend in surprising ways. Time and space, once thought fixed, become flexible. One person's now may not be another's. You can feel this in your daily life, though subtly. When you send a message to a friend across the globe, you may both imagine you're having a conversation now. But in fact, what you call now and what they call now are separated by thousands of kilometers, by delays of signals and processing. At everyday speeds, the difference is tiny, almost invisible, but at cosmic scales, it becomes profound. Imagine two stars exploding in different galaxies. To us on Earth, they might seem to flare at the same moment. To another observer, flying past in a distant galaxy, one may come first, the other much later. There is no absolute order that all can agree on. The universe does not keep one single time. It offers each observer their own slice. This might sound unsettling. After all, we live our lives as if there is one clock, one present moment shared by all. But perhaps it is also freeing. It means reality is more like a woven fabric than a straight line. Each thread of experience runs alongside others, intersecting here and there, but never quite forming a universal now. Einstein's insight reshaped physics completely. Before him, Isaac Newton had imagined space and time as a fixed stage, immovable, steady, the same for everyone. Einstein revealed that the stage itself bends and shifts, depending on how you move. Light sets the rule, and the universe obeys. Think of it like this. If two friends are knitting scarves side by side, but one knits faster, their rows will not line up. Both scarves are real, both continuous, but the timing of stitches differs. Reality works the same way. Each of us is knitting our own timeline. They may align in places when we meet, talk, or share a laugh. But beyond those points, the alignment fades. This relativity of time has been tested in clever and beautiful ways. One involves tiny particles called muons, created high in the atmosphere when cosmic rays strike air molecules. Muons live for only a fleeting moment, so by rights they should decay long before reaching the ground, and yet we detect them at Earth's surface. Why? Because from our perspective, their internal clocks run more slowly as they race toward us at near light speed. Their lives are stretched, long enough for them to arrive. To the muons themselves, no magic occurred. Instead, they feel the distance they travel is shorter than we measure it. Both stories are true, depending on your frame of reference. This is reality under relativity. Each viewpoint is valid, but there is no single master version. Time and space adapt to the observer. We see this too in the faraway glow of quasars, the brilliant hearts of galaxies. Their flickering light stretches as it travels across billions of years. When astronomers study these signals, they see cosmic time dilation, events unfolding more slowly than they would close by. The very heartbeat of the universe changes tempo depending on where you sit in the audience. And in the strangest theatre of all, the edge of a black hole, time nearly stops. To a distant observer, anything falling toward the black hole slows, freezes, caught in slow motion. But for the falling traveller, time ticks normally, right up until the final plunge. One story of time from the outside, another from the inside. Both real, yet forever divided. If you lie in bed now, listening to this, you might glance at the clock on your wall and think, this is the time. But remember, your head is a fraction farther from Earth's centre than your feet. Relativity tells us that means time at your head flows just slightly faster than time at your feet. Not enough to notice, not enough to live two lives at once, but enough that physicists with sensitive clocks can measure it. You're a being stretched across tiny gradients of time, even as you drift into sleep. What does this mean for reality? It means that now is not a cosmic constant. The present moment is local, personal, stitched to your motion and your place. There is no master switch that declares the present for all. Reality is a patchwork of overlapping times, each observer carrying their own rhythm. Perhaps that makes the world even more wondrous. You and I, sharing this story right now, are part of a vast tapestry of moments. Somewhere, a star is collapsing, its light yet to reach us. Somewhere else, a child is seeing their first snowfall. Their now and yours are real, but not aligned. And that is perfectly fine. Reality does not need one universal clock. It is all clocks, all moments, gently woven together into a fabric of experience. So, as you feel the seconds passing, remember, time is not absolute. It is elastic, flexible, woven differently depending on your path. And in that flexibility lies a deeper truth. Reality is not a stage set in stone. It is a dance of perspectives, each valid, each essential, each fleeting as a passing train. The idea that each of us carries our own personal slice of time may already feel dreamlike. But relativity is not just a poetic metaphor. It is real, measurable, and it shapes the very technology you use every day. Time does not tick at the same pace for everyone, everywhere. And sometimes that difference is the very thing that keeps our modern world from falling apart. Think first about your phone. Each time you use a navigation app, it quietly consults a constellation of satellites orbiting above the Earth. These satellites carry atomic clocks, ticking with exquisite precision. But here's the curious part. Those clocks do not keep time in sync with yours on the ground. Because the satellites are farther from Earth gravity and moving at high speed, their time runs at a slightly different pace. If engineers ignored relativity, your GPS directions would drift, leading you astray by kilometers every single day. The fact that you arrive safely at the cafe or your friend's house is proof that relativity isn't an abstract curiosity. It is stitched into the very fabric of your morning commute. This slowing and stretching of time shows up in nature too. Remember the muons, those tiny particles raining down from the sky? To a physicist, they are like travellers with impossibly short visas, particles that should vanish before they can arrive, but somehow linger long enough to reach the ground. From our perspective, their clocks slow down as they speed toward us at nearly the speed of light. Their lifetimes stretch, letting them survive the trip. But from the muon's perspective, no magic occurs. Instead, the distance between the atmosphere and the Earth shrinks for them. Space itself contracts in the direction of their travel. To them, the journey is shorter. Two perspectives, both true, both describing the same reality. It's as though the universe gives each traveller a trade. Move faster, and your time slows, but your path becomes shorter. What you lose in one direction, you gain in another. The balance is perfect, always preserving the constancy of light speed. You might imagine it like walking along a stretch of elastic fabric. If you take long strides, The fabric stretches beneath you, and your steps cover more ground. But if someone else stands still, they see you moving strangely, your steps slowed, your path compressed. The reality is not one or the other, it is both, depending on where you stand. The universe displays these distortions not only with particles and satellites, but on grander cosmic stages. When astronomers watch distant quasars, the brilliant hearts of galaxies powered by supermassive black holes, they notice something strange. Their flickering, their rhythms appear stretched out compared to what we expect. The very heartbeat of these cosmic engines runs more slowly when viewed from across the abyss of space. Light travelling billions of years carries with it the marks of cosmic expansion and time dilation, whispering that time itself flows differently depending on where and when you observe it. Perhaps the most dramatic demonstration of all comes from black holes. Imagine floating near one close enough to feel its pull. To you, time continues as usual. Your heart beats, your watch ticks, your thoughts unfold. But to someone watching from far away, your movements slow, your signals stretch, until you seem frozen at the edge, suspended in eternal twilight. From their perspective, you never cross the boundary. From yours, you fall straight through. Both accounts are true, but they cannot be merged into one. Reality, once again, refuses to grant us a single universal picture. Even closer to home, the Earth itself teaches us this lesson. The stronger the pull of gravity, the more time slows. If you placed a clock at sea level and another on a mountain, the one on the mountain would tick ever so slightly faster. Your own body lives across a gradient. Your head, being farther from the Earth's centre, ages imperceptibly faster than your feet. The difference is tiny, fractions of a second across a lifetime, but it is real. You are, quite literally, a being stretched between two times. This idea, though rooted in equations and experiments, has a quiet poetry to it. We often talk about time as if it were a steady river, flowing the same for all. Relativity reveals that the river twists, eddies, and branches. Each traveller carries their own current. Sometimes those currents align, sometimes they drift apart. The beauty is that the laws of nature embrace all of them, so the next time you check your phone and watch the little blue dot guide you to your destination, remember that hidden inside are the corrections of relativity. The engineers who built it had to bow to Einstein's insight, adjusting for time that runs differently in orbit than on the ground. Each safe arrival is a quiet tribute to the flexibility of reality, and perhaps, when you glance at the night sky, you can think of those moons streaking through the atmosphere, living longer than they should, their tiny lives stretched by speed itself. Or imagine a quasar blinking slowly, its heartbeat stretched by billions of years of cosmic travel. Or picture yourself standing on a cliff, knowing your head is racing ever so slightly ahead of your feet in time. All of it true, all of it part of the same strange, beautiful universe. Relativity teaches us that space and time are not rigid backdrops. They are participants in the play of reality, bending and adapting, slowing and stretching, to keep the universe consistent. The speed of light is the rule, and from it flows a world far stranger and more wondrous than the everyday clock face suggests. So, as you lie here now, listening, feel the seconds passing. Know that they are not absolute. They are personal, local, woven into your place and your motion. The tick of your clock, the beat of your heart, the rhythm of your breath. These are your own measures of time. They may stretch or shrink compared to another's, but they are real for you. And in that realization lies a kind of comfort. Reality is not fixed and indifferent, but flexible, responsive, alive with relativity. So far, we've seen how time itself bends and stretches, refusing to stay the same for all observers. But Einstein's insight didn't stop there. In 1915, he revealed an even deeper twist: gravity. The very force that holds you against your bed as you listen now is not what we once thought. It isn't an invisible tugging force at all. Instead, it is the shape of space and time themselves. To understand this, imagine the universe not as a cold void, but as a vast, flexible fabric. It may be invisible, but it can stretch, bend, and ripple. Every object with mass, from an apple to a planet, presses into that fabric, creating a dent. Place a bowling ball on a trampoline and you'll see the cloth dip. Roll a marble nearby and it will curve inward, not because the ball pulls on it, but because the marble is simply following the curves in the surface. This is the picture Einstein gave us. Planets orbit the Sun, not because the Sun tugs at them with some unseen rope, but because the Sun creates a deep valley in the fabric of space-time, and the planets are rolling along the curves. It's a simple metaphor, and yet profoundly strange. Gravity, which feels so solid and direct in our daily lives, becomes something almost ghostly. You aren't pulled to the ground by Earth's hands. You're following the straightest possible path through the bent geometry around you. Your body, your bed, the floor beneath it, all are pressed into the same invisible bowl, and that bowl is what keeps you close. You can test this yourself in small, everyday ways. Think of a tossed ball arcing through the air. Newton would describe it as the Earth pulling the ball downward with a force. Einstein would say the ball is simply following a curved trajectory through bent space-time. Both explanations lead to the same prediction, but Einstein's view reveals why light itself, which has no weight at all, also bends when it passes near massive objects. Light cannot be pulled, but it must follow curves. This bending of light was one of the first great proofs of relativity. In 1919, during a solar eclipse, astronomers observed stars appearing slightly shifted in the sky as their light grazed past the Sun. The Sun's mass curved space-time, and the light bent along the curve, just as Einstein predicted. Newspapers declared it the triumph of a new physics. Suddenly, the world knew that space and time were not fixed backdrops, but living, flexible participants in the universe. And it doesn't stop at gentle curves. Massive stars collapsing into black holes can bend space so steeply that nothing, not even light, can climb back out. Around these invisible abysses, space-time folds like a waterfall plunging over a cliff. Closer to home, even our own Earth bends space-time just enough that satellites and clocks must adjust for it. Every time your GPS works, every time an image of a distant galaxy is magnified by a cosmic lens, you're seeing the fingerprints of curved reality. If this feels abstract, imagine lying on a soft mattress. Place a heavy book near your side and feel the dip. If you roll a marble across the sheet, it curves around the depression. This is space-time beneath your feet, beneath your bed, beneath the Earth itself. You're always moving along curves, even when you feel still. The beauty of Einstein's vision is that it connects motion, mass, and time in one smooth fabric. Stand near a massive mountain, and time itself runs more slowly than on the open plain. Send light across a galaxy, and it will bend like a river winding through hills. Even the empty vacuum of space is not rigid. It can ripple with gravitational waves, like the faint tremors of distant cosmic collisions. In 2015, a century after Einstein's prediction, we finally detected those ripples, faint vibrations from black holes colliding billions of light years away. Reality itself rang like a cosmic drum, and we heard its echo. Yet, for all its strangeness, general relativity is also quietly comforting. It says the universe has rules, graceful and consistent. Mass tells space-time how to curve. Space-time tells matter how to move. You can see it in the orbit of the moon, the tides rising on shores, the fall of a dropped apple. Every motion is the choreography of curves, the softest of rulers guiding everything without a sound. Next time you lie in bed, feel your body sink into the mattress. That sensation is gravity, yes, but also geometry. You're not held down by force, but guided by the curves of the Earth's presence in space-time. The apple that rolled off your desk today, the moon that pulls the seas, the galaxies wheeling in the night sky. They're all dancers in the same choreography, tracing paths on the same invisible sheet. So, when you think of reality, don't picture a stage built of rigid walls and ticking clocks. Picture instead a fabric, soft, flexible, responsive, bending gently beneath every step. That is the fabric beneath your feet, the quiet stage on which every story unfolds. And in its silent curves lies one of the deepest truths we know. Reality is not what it seems, but it is profoundly, beautifully ordered. We've wandered across the curves of space-time, seen how planets orbit like marbles on a trampoline, and how light bends along invisible valleys. But let's return to something closer, something you can hold in your hand. That apple again, or the chair beneath you, or even your own body. They all feel solid. You can knock on wood, lean against a wall, clench your fist and know it is there. Yet science tells us that solidity is not what it seems. Beneath the surface, matter is a world of vast emptiness, fragile boundaries, and particles that behave like restless ghosts. At the dawn of the 20th century, scientists already knew about atoms, those supposed indivisible units of matter. They imagined them as tiny solid spheres, like billiard balls too small to see, stacking together to make up everything. But that picture began to unravel when physicists performed a simple yet profound experiment. Ernest Rutherford and his colleagues aimed a thin beam of particles at a sheet of gold foil. If atoms were solid little beads, those particles should have passed straight through or bounced off with small deflections, and most did. But every so often a particle shot back at a sharp angle, as if it had struck something incredibly dense. Rutherford was astonished. It was, he said, like firing a bullet at tissue paper and having it bounce back at you. From this came a new vision. Atoms are not solid balls. They are mostly empty space, with nearly all their mass concentrated in a tiny central nucleus. Electrons swirled around that centre, so far out that, proportionally, the atom was like a cathedral with a grain of sand in the middle. Imagine walking into a vast, echoing hall, its ceilings soaring, its walls stretching into shadow, and at the very centre, a single speck of dust. That is the structure of the atom, and everything. Apples, chairs, mountains, you, is made of such cathedrals. The nucleus itself is a marvel. Protons and neutrons huddle together, bound by the strong nuclear force, one of nature's most powerful yet most intimate interactions. Without it, the positive charges of the protons would repel each other and the nucleus would fly apart. But the strong force holds, stronger than repulsion, tighter than our intuitions allow. Inside the protons and neutrons are quarks, bound by gluons in an endless jittering dance. We never find quarks alone. They're always stitched together, like threads in a tapestry that can never unravel. This emptiness inside atoms doesn't mean matter is fragile or ghostly in practice. It means that what you experience as solid is actually the result of forces, not substance. When you press your hand against the table, the electrons in your skin repel the electrons in the table. You're never truly touching it, not in the sense of one surface colliding with another. You're hovering a whisper away, held back by invisible electric fields. Solidity is a sensation your brain interprets from resistance, not a literal stacking of solid blocks. If you could somehow remove all the empty space from within the atoms of your body, compressing the nuclei together, you would shrink to something unimaginably tiny, smaller than a grain of sand, yet still weigh the same as you do now. You would become a speck of matter so dense it would rival the collapsed stars we call neutron stars. The idea is absurd and frightening and also humbling. You're mostly emptiness, structured by fields and forces, not bricks and mortar. It can be unsettling to realise that the solidity of the world is an illusion. But perhaps it's also comforting, because illusions can be reliable. The chair still supports you. The apple still crunches when you bite. Reality does not fail, even if it is stranger than your senses suggest. And yet, the atom story does not stop with emptiness. Electrons, those tiny companions whirling around the nucleus, refuse to behave like planets orbiting a sun. They blur into clouds of probability, spreading across space like mist. Their exact positions cannot be nailed down. They exist as possibilities, waves of chance, until interaction collapses them into a definite place. You cannot draw neat little circles to map them. You can only describe where they are likely to be. This was one of the first clues that reality is not a simple stage of tiny balls bouncing about. It is a world of probability, waves, and uncertainty. To say, this is where the electron is less accurate than saying this is where the electron might be. An atom, then, is not a tidy cathedral of fixed stones, but a cathedral filled with fog, with echoes, with probabilities waiting to become real. Pause for a moment and think of your own body. Billions of atoms, each mostly empty space, each nucleus a tiny island of mass, each electron smeared into a misty cloud. You're made not of solidness, but of patterns, arrangements of fields and forces that only feel solid to the mind that perceives them. It is easy to forget this when you walk, eat, or type on a keyboard. The everyday world feels so firm, so trustworthy, and yet, beneath the trust lies emptiness and uncertainty. You're a cathedral of atoms, each one a cathedral of its own. Within you are the same mysteries found in stars and galaxies in all the universe. So perhaps the lesson is this: reality need not be what it seems to still be real. The apple is still delicious, the chair is still sturdy, your heartbeat still steady. The illusions of solidity serve you well. But knowing what lies beneath, emptiness, forces, clouds of probability, reminds us that reality is not a single layer. It is a layered dream, stable enough to live in, yet strange enough to astonish. And when you close your eyes, perhaps you can imagine those cathedrals within you. Vast, echoing spaces, tiny specks of mass at their hearts, mists of probability floating around them, silent, invisible, and yet quietly real. If atoms are vast cathedrals, empty but for specks of mass and drifting clouds of electrons, then what holds those cathedrals together? Why doesn't the atom simply collapse, with electrons spiraling into the nucleus like moths falling into a flame? For that answer, we step into the strange world of the quantum, the world where energy comes in tiny indivisible packets, where matter behaves like both particle and wave, and where certainty dissolves into probability. At the turn of the 20th century, a quiet revolution began with something as ordinary as heat. Physicist Max Planck was studying how objects glow when heated. You've seen it yourself. An iron rod glowing red in a forge, or a light bulb filament glowing white. Classical physics said this glow should become infinite at higher frequencies, an absurd prediction. To solve the puzzle, Planck proposed that energy isn't continuous like water flowing from a faucet. Instead, it comes in discrete packets, quanta. A light wave, for instance, is made not of a smooth stream, but of tiny lumps of energy, later called photons. This was the first step into a new world, one where reality at small scales obeys different rules than the ones we see each day. Soon after, Niels Bohr imagined electrons not as spiraling moths, but as travellers on specific orbits, like planets moving in fixed lanes around a star. They could leap from one orbit to another, but never linger in between. These quantized jumps explained why atoms glow with precise colours, why neon signs shine red and sodium lamps glow orange. The electrons move, release photons, and light is born. but the story grew stranger. In 1924, Louis de Broglie, a French prince turned physicist, suggested that matter itself behaves like a wave, not just light, but electrons, protons, everything. Imagine throwing a pebble into a pond, the ripples spreading outward. Now imagine those ripples are not water, but the particle itself. Where is the particle? Everywhere the ripple spreads. Where does it land? Only when you look, only when it interacts, does the ripple collapse into a definite spot. This was confirmed when electrons were sent through two slits in a barrier. Instead of forming two neat piles on a screen, they formed an interference pattern, ripples of light and dark, just like waves on water. Yet when the experiment was done one electron at a time, the pattern still emerged. Each electron alone seemed to travel like a wave through both slits, interfering with itself, then landing as a particle in one place. It is a riddle. How can something be both wave and particle, both everywhere and somewhere, both mist and marble? Erwin Schrödinger offered a way to describe this. The wave function, a mathematical cloud representing the probabilities of where a particle might be. His famous thought experiment of the cat in a box illustrates the strangeness. Until observed, the cat is both alive and dead, suspended in a blur of probabilities. Of course, no cat is really both at once, but the image shows the unsettling truth. At the quantum level, reality is not fixed until interaction makes it so. Werner Heisenberg added another twist: the uncertainty principle. The more precisely you know one aspect of a particle, its position for instance, the less precisely you can know its momentum. Nature does not allow perfect knowledge. Reality itself keeps some secrets hidden, not because our instruments are clumsy, but because uncertainty is woven into the fabric of existence. All of this sounds dizzying, but pause and think how much of your life depends on it. The way your phone screen lights up, the way computers compute, the way atoms bond into molecules, all rest on quantum rules. The glow of neon lights, the stability of your chair, the beating of your heart. They all rely on electrons leaping between energy levels, photons carrying energy, wave functions guiding behavior. You live every moment inside quantum reality, even if it feels invisible. Perhaps the strangest part is that the quantum is not somewhere else hidden far away. It is here, in the apple you sliced earlier. Every electron in its atoms hovers in probability clouds. Every photon bouncing from its surface is a quantum packet. You're not apart from the quantum, you're built from it. So when you touch the apple, or glance at your phone, or look at the stars, remember, beneath every ordinary thing lies a blur of probabilities, a dance of quanta, a mist of waves that sometimes pretend to be particles. Reality at its core is not a tidy stage, but a restless theatre of possibilities. And yet, for all its strangeness, this quantum theatre is reliable. The apple stays whole, the chair stays solid, the stars burn steadily. Probability does not mean chaos. It means order of a different kind, a soft statistical order that underlies the everyday world. Take comfort in this. The uncertainty of electrons is the certainty of chemistry. The wavering of photons is the stability of light. The probabilities of the quantum give rise to the certainties of life. As you drift tonight, think of yourself not as a solid creature, but as a constellation of clouds, rippling waves, shimmering probabilities. You are, in a very real sense, a walking quantum experiment carried out endlessly, effortlessly, beautifully by the universe itself. If quanta already seem slippery, behaving like both waves and particles, then prepare for an even stranger friendship, one that stretches across space, laughs at distance, and defies our common sense of separation. It is called entanglement, and to many physicists it feels like reality's quiet rebellion against the idea of independent things. The story begins with a puzzle posed by Albert Einstein himself, alongside Boris Podolsky and Nathan Rosen in 1935. They imagined two particles that once interacted and then flew apart. According to quantum theory, their properties could become linked, entangled, so that measuring one instantly told you something about the other, no matter how far away it travelled. Einstein called this spooky action at a distance. He was uneasy with it, convinced that quantum mechanics must be incomplete, that hidden information somewhere must explain the connection. Surely the universe couldn't be so strange. But experiments said otherwise. Time and again, physicists tested entangled particles, sending them down different paths, sometimes kilometers apart. When they measured one particle's property, say its spin, the other particle's spin was instantly correlated, even though nothing could have travelled between them in time. It was as if two coins, flipped in separate cities, always landed in opposite states. Heads here, tails there, even though neither coin knew in advance how it would land. John Bell in the 1960s sharpened the puzzle. He derived inequalities, mathematical tests, that could distinguish between Einstein's idea of hidden variables and the full strangeness of quantum mechanics. The experiments, carried out over decades and culminating in a Nobel Prize in 2022, consistently confirm the quantum view. Entanglement is real. Nature does not follow the neat separations our intuition prefers. Pause for a moment with that thought. Two particles, separated by oceans of space, yet still acting as if they share a single identity. It isn't that one particle sends a message to the other faster than light. It is that the very idea of them being separate is incomplete. They are two notes of the same chord, even when played on instruments far apart. To picture it, imagine a pair of dice enchanted by some magician. Roll one in Paris, roll the other in Tokyo, and no matter what, they always add to 7. Each die alone seems random, but together they reveal a hidden harmony. Or think of two dancers who once moved together, then separated to opposite sides of the stage. Even apart, their movements still mirror one another, as if guided by some invisible score. Of course, entanglement isn't magic. It doesn't let you send messages faster than light. You can't whisper across the cosmos with it. The randomness of each individual measurement preserves the universe's deeper rules, but the correlations are undeniable, reminding us that distance and separation are not as absolute as we once believed. And entanglement isn't rare. It happens constantly, in labs and in nature. The photons streaming from the sun are born entangled in pairs. The electrons in the atoms of your body are entangled with each other, their spins linked in delicate balances. Quantum computers, now in their infancy, rely on harnessing entanglement to perform feats of calculation impossible for ordinary machines. Entanglement is not an exotic exception. It is woven into the fabric of what is real. What does this say about reality? At the very least, it suggests that reality cannot be reduced to independent parts, each with its own self-contained story. Instead, reality is relational. Things exist not in isolation, but in connection, like threads in a single woven cloth. Pull on one end, and the patterns shift everywhere. This echoes something we sense in our own lives. You are not an island, but a web of connections. Family, friends, culture, language. The meaning of a smile, a word, a song comes from its relation to others. In the same way, particles themselves may be less like solitary marbles and more like relationships etched into the universe. Einstein, who distrusted entanglement, once asked if the moon exists only when we look at it. Most physicists today would answer yes, the moon exists on its own. But entanglement reminds us that existence is not always so simple. At the quantum level, observation, relation, and outcome are braided together in ways that challenge our intuition. Reality, it seems, is not a collection of separate things, but a set of correlations, a dance of connections. And perhaps there is comfort in that, because it means that separation is not as sharp as we fear. Even when things drift apart, they can remain linked. A photon flying 1 billion light years may still carry a connection to its twin. A human being, separated from others by oceans or silence, is still connected through shared rhythms, shared experiences, shared reality. Entanglement is a whisper that the universe itself values relationship. So tonight, as you lie there, imagine those entangled particles born together and now far apart, still mirroring each other in silence. Imagine yourself as part of a larger whole, your atoms linked by the same laws, your existence entangled with the stars that forge the elements within you. You're not separate from the universe, you're a note in its great chord, resonating with others in ways both obvious and unseen, and that, in the gentlest sense, is what entanglement teaches us. That reality is not only matter and energy, but also relationship and pattern. A cosmos less of isolated dots, more of constellations, where distance is softer than it seems, and where even across vastness, a strange friendship endures. We've opened the cathedral of atoms, seen its emptiness, and glimpsed the tiny speck of mass at its centre. But if the nucleus is the heart of the cathedral, then the electrons that surround it are like restless spirits, never still, never fully where you think they should be. Their behaviour ushered in one of the strangest, most beautiful revolutions in science, the quantum revolution. It began with a puzzle about light, but it soon revealed a universe where certainty dissolves into maybes and matter itself hums like a wave. At the dawn of the 20th century, light was thought to be a continuous wave, flowing smoothly like ripples on a pond. But Max Planck, puzzling over how objects glow when heated, proposed something shocking. He suggested that light's energy came in discrete packets, quanta, like coins that can't be split. You can't have half a coin, and light too seemed to come in lumps. These packets were later called photons. Imagine turning the dimmer switch in your living room. Instead of a smooth slide, nature adjusts the brightness in tiny clicks, steps too small for your eyes to see, but fundamental all the same. Soon after, Niels Bohr applied this strange discreteness to the atom. Electrons, he suggested, don't whirl randomly around the nucleus like moths near a flame. Instead, they occupy specific orbits, like rungs on a ladder. They can leap between these orbits, but never hover in between. When they fall to a lower rung, they release energy as light. This explained why atoms glow with specific colours. Neon shines red, sodium lamps glow orange, and hydrogen emits a soft violet. Each element sings its own tune, because its electrons can only dance on particular steps. But reality had another twist in store. In 1924, Louis de Broglie, a French aristocrat with a taste for bold ideas, proposed that matter itself has waves. Electrons, he said, could behave like ripples spreading on a pond. It sounded absurd. How can a particle be a wave? But the experiments confirmed it. When beams of electrons were fired at thin crystals, they created rippling patterns on a screen, exactly like light waves passing through a slit. Particles, it turned out, were also waves. To picture this, imagine tossing a stone into a lake. The ripples spread outward, soft and circular. Now imagine those ripples are not water, but the very electron itself. Its presence smeared across space, neither here nor there, but potentially anywhere the wave spreads. Only when you dip your hand into the water does the ripple collapse into a single splash. That is what it means for an electron to be both particle and wave. This strange duality is most famously revealed in the double-slit experiment. Fire electrons one at a time through two narrow slits, and you'd expect them to make two tidy lines on a screen. Instead, they interfere like waves, creating a pattern of stripes. Even stranger, each single electron seems to go through both slits at once, interfering with itself, until you look to see which slit it chose. The moment you observe, the wave of possibility collapses, and the electron behaves like a simple particle. Reality, it seems, cares whether you're watching. Erwin Schrödinger gave us a way to describe this shimmering uncertainty. He imagined the electron not as a marble orbiting a nucleus, but as a cloud of probability, a wave function that spreads through space. The cloud describes all the places the electron could be. The act of measurement squeezes the cloud into a point, collapsing maybes into one actual is. It was Schrödinger too who illustrated this with his famous cat-in-a-box thought experiment. The cat, linked to a quantum event, is alive and dead at once until observed. Of course, no real cat is both alive and dead, but the story shows how strange it feels when probabilities blur into reality. To this, Werner Heisenberg added his principle of uncertainty. The more precisely you know where something is, the less precisely you can know how fast it's moving, and vice versa. Nature does not allow perfect knowledge, not because we lack skill, but because reality itself refuses to reveal all at once. It is as if the universe insists on keeping some secrets, leaving us with shadows instead of sharp outlines. Max Born offered a way to read this. The wave function is not a physical wave of matter, but a wave of probability. It tells us where the electron might be, where it might land if measured. Nature does not whisper yes or no. It whispers maybe. The world at its core is not rigid but probabilistic. You might think this makes reality fragile or uncertain, but in truth it makes it rich. The probabilities average out into the stable, dependable world you know. The solidity of a chair, the crispness of an apple, the rhythm of your heartbeat, all emerge from the swirling uncertainty below. Order is built from maybes. If you pause and look around your room, every lamp, every colour on the wall, every bite of food you've ever eaten owes itself to this quantum strangeness. Your phone screen glows because electrons leap between quantized states, releasing photons. The chemistry of life is possible because electrons blur into clouds, binding atoms in flexible, delicate patterns. Without the whispers of maybe, there would be no certainly. And yet the quantum world is not merely useful, it is also quietly beautiful. Think of a violin string vibrating to create a note. That vibration is quantized too. It can only resonate in certain patterns. The same is true of electrons, orbiting in standing waves around a nucleus. Reality itself is musical, with atoms singing in discrete notes. So, as you drift tonight, picture yourself as part of this symphony. Your body is not a rigid machine, but a shimmering orchestra of probabilities, each atom humming with quantized energy, each electron a ripple of possibility. The world around you is not solid stone, but a melody of quanta, waves rising, collapsing, rising again, and in that melody lies a soft reassurance. Uncertainty does not mean chaos, it means possibility. The future is not carved in stone but written in probabilities, unfolding moment by moment, like ripples on water, like music on air, like the soft whisper of maybe that has built everything you've ever known. Time, so 1.5. The quantum world is already filled with whispers of uncertainty, particles that behave like waves, and probabilities that only become definite when we look. But perhaps its most bewildering secret is a kind of invisible connection, a strange bond that ignores distance and challenges our sense of separation. This bond is called entanglement, and it is one of the most quietly astonishing discoveries in all of science. The idea first appeared in 1935, when Albert Einstein, Boris Podolsky, and Nathan Rosen published a famous paper now remembered as the EPR paradox. They considered two particles born together, then sent flying apart. According to quantum mechanics, certain properties of these particles, like their spins, would remain linked no matter how far they travelled. Measure one particle, and the other's outcome is instantly determined. Einstein did not like this at all. He called it Spukhaft Fernwirkung, spooky action at a distance. Surely, he thought, quantum theory must be incomplete. There must be hidden information guiding the particles, something we just hadn't discovered yet. But the decades that followed revealed something even stranger. The universe really is this spooky. In the 1960s, physicist John Bell sharpened the debate with a set of mathematical tests. now known as Bell's inequalities. These inequalities drew a clear line. If reality were governed by hidden variables, the results of certain experiments would stay within predictable bounds. But if quantum entanglement were real, those bounds would be broken. The experiments were carried out again and again with ever greater precision, and the results were undeniable. Entanglement is real. In 2022, the Nobel Prize in Physics was awarded to Alain Aspect, John Clauser, and Anton Zeilinger for their groundbreaking experiments confirming these entangled connections. Across fibres, across laboratories, even across kilometres of open air, entangled particles defied Einstein's hidden variable comfort. Nature, it seems, does not obey our classical intuitions. To picture entanglement, imagine a pair of magical dice. Roll one in New York and the other in Tokyo, and no matter how many times you roll, the results always line up. Say, they always add to 7. Each die seems random, but together they reveal a pattern. It isn't that one die sends a signal to the other faster than light. It's that the two are not truly separate. They're parts of the same underlying reality, even when distance lies between them. Another way to imagine it, think of two dancers who once practiced side by side, moving in perfect unison. One goes to the east of the stage, the other to the west. When the music plays, their steps still mirror one another, not because they shout across the floor, but because the choreography binds them both. Entanglement is like that choreography written into the universe itself. Of course, entanglement doesn't mean you can send secret messages faster than light. Each individual measurement still looks random, unpredictable. Only when you compare results later do you see the correlations. The universe preserves its cosmic speed limit, but it also whispers a reminder. Separation is not as absolute as we thought. What's more, entanglement isn't rare or exotic. It happens naturally all the time. The light streaming from the sun often emerges in entangled pairs of photons. The electrons in the atoms that make up your body are entangled with each other, balancing spins in delicate pairs. Quantum computers, those strange machines just beginning to take shape, depend on entanglement to link their quantum bits, unlocking calculations ordinary computers could never dream of. Far from being a rare oddity, entanglement is woven into the fabric of existence, present in the warmth of sunlight and the bonds of matter itself. So what does it mean for reality? At the very least, it tells us that the world cannot be understood as a collection of separate parts, each independent and self-contained. Instead, reality is relational. Things exist in connection, not isolation. Particles are not little marbles sitting apart, but notes in a larger chord, threads in a wider weave. And in that sense, entanglement reflects something we already know in our human lives. No one exists alone. We are born into families, communities, cultures, languages. A smile means something only because it is shared. A song exists only when heard together. Entanglement is nature's way of reminding us that connection runs deeper than appearances, that the universe itself is, at its core, relational. Einstein once wondered whether the moon exists when no one looks at it. Most physicists would say yes, of course it does. But entanglement nudges us to admit that reality is not always about independent objects waiting to be observed. Sometimes it is about the relationships between things, the invisible threads tying them together. And perhaps that is the most soothing thought of all, that even across impossible distances, even when two things drift apart, they can remain connected. A photon travelling across the cosmos may still carry an invisible bond with its twin, and you, lying here listening, are made of atoms whose histories are entangled with stars, with galaxies, with the universe itself. You're not separate from the cosmos. You're a continuation of its story, linked by laws that value connection. So as you close your eyes tonight, imagine those entangled particles, tiny silent companions, flying apart yet never truly apart. Imagine yourself as part of that same web, a node in a grand network that spans the stars. Distance may feel large, but in reality's deepest fabric, nothing is ever entirely alone. Entanglement is the universe's gentle reminder that friendship, connection, and relation are not accidents. They are part of what it means to be real. We've travelled from the emptiness of atoms to the rippling waves of probability and the quiet strangeness of entanglement. Each step has shown us that matter is not what it first appears, and yet we can peel back one more layer. For beneath particles and their odd behaviour lies a deeper truth. Particles are not the foundation at all. They're excitations, ripples, brief actors stepping onto a stage that is far older and more fundamental. That stage is the field. In the language of modern physics, every kind of particle we know, electrons, photons, quarks, neutrinos, is an excitation of some underlying field. Imagine an ocean stretching endlessly in every direction. Most of the time, it is calm, silent, and flat. But when energy stirs it, ripples rise. Those ripples are what we see as particles. The field is the stage, and the particles are the actors that appear, perform, and then fade back into the quiet. For example, take light. A photon is not a tiny marble shooting through space. It is a ripple in the electromagnetic field, a brief quiver of energy passing through an invisible medium that fills all of space. The electron too is not a solid bead, but a ripple in the electron field. Quarks are ripples in the quark field. Gluons, the messengers of the strong force, are ripples in the gluon field. Everywhere you look, everything is at its root a ripple. This picture is called quantum field theory, QFT for short, and it is one of the most successful frameworks in all of science. It explains why atoms are stable, why light interacts with matter, why nuclear reactions release such immense energy. It is the silent foundation beneath everything, so reliable that we almost forget it's there. To make this less abstract, imagine a surfer. The ocean is vast and unseen until it rises into a wave. The surfer cannot ride the ocean itself, but only the crest, the ripple. In the same way, we do not touch the field itself, but the ripples it sends our way. You're not made of particles so much as you're made of waves caught in motion, excitations that briefly give the illusion of solidity. And there is something almost poetic in this, because if fields are the stage, then the universe is less a collection of things than it is a play of performances. Each electron, each photon, each particle is a temporary actor, stepping forward to play a role, then bowing and dissolving back into the field. What we call reality is the endless improvisation of these appearances, a drama that has been running since the beginning of time. Consider the neutrino, one of the strangest actors on this stage. Trillions of them pass through your body every second, born in nuclear reactions in the sun, in supernovae, in the deep furnace of stars. They are ripples in the neutrino field, nearly invisible, rarely interacting, yet everywhere. You never feel them, never sense them, yet they are part of you, weaving silently through your existence. Or consider the gluon field, which binds quarks together inside protons and neutrons. Without it, the nucleus would fall apart and atoms could not exist. The gluon field is like a powerful glue woven into the stage itself, keeping the actors bound to one another, ensuring the performance continues. And of course, there is the photon field, the electromagnetic field, which gives rise to light, radio waves, X-rays, all the forms of radiation we know. Without it, there would be no sight, no warmth, no communication. Your very ability to hear this story through a device depends on the gentle cooperation of the photon field, carrying information across invisible ripples. So when you look at the night sky, what you are really seeing is not objects in the old sense, but ripples rising in cosmic fields. Stars are bundles of excitations, planets are arrangements of bound ripples. Your body itself is a choreography of fields. You are a ripple among ripples, an actor among actors, performing on a stage so vast you cannot see its edges. This might sound abstract, but pause for a moment and imagine yourself at the beach. The waves rise and fall, each unique, each temporary. Yet the ocean beneath is constant, silent, holding them all. That is what quantum fields are like. You are one of the waves, brief, beautiful, carried along by something greater. And the symmetry of it is striking. Every particle we know has a corresponding field. Every actor has a stage. Together, they form what physicists call the Standard Model, a kind of periodic table, not of elements, but of fields and their excitations. It is one of the most accurate and tested frameworks in science, and it describes reality with astonishing precision. Yet, like all stages, it leaves us with mysteries. Why these actors and not others? Why these fields and not more? The Standard Model works, but it does not feel complete. Perhaps the stage is larger than we realise and new actors wait in the wings. For now, though, it is enough to know that beneath the atoms of your body, beneath the particles you've heard named in school, lies this quieter, deeper truth. Fields are the true foundation. Particles are the ripples, the waves, the fleeting excitations. The fields are the ocean, endless and unseen. So as you rest tonight, imagine yourself not as a rigid structure of matter, but as a pattern of ripples moving on invisible seas. The ocean is silent, the waves rise and fall, and for a little while you are one of them, an actor upon the stage of fields, woven into the performance of reality. We've pictured fields as the great stage of reality, with particles as ripples that rise and fall. But there is one field that plays a special, almost mysterious role. Without it, the actors would rush across the stage weightless, like shadows with no substance. Without it, matter as we know it would not exist. This is the Higgs field, often called the field that gives mass, sometimes even called the God particle. In the headlines, though scientists tend to smile politely at that exaggeration. The Higgs field fills all of space, invisible and universal, a kind of background presence that every particle must wade through. To imagine it, think of a dance floor coated in thick molasses. As dancers move, they are slowed. They acquire resistance, they feel heavy. In empty space without the Higgs field, particles like electrons would have no mass, zipping about at the speed of light. But with the Higgs field permeating everything, they feel drag, resistance, and thus acquire the property we call mass. Mass is not a gift carried from within, it is the result of interacting with this invisible ocean of molasses. In 2012, at CERN's Large Hadron Collider, scientists confirmed this idea by detecting the Higgs boson, a fleeting ripple in the Higgs field itself. It was a triumph decades in the making, the last missing piece of the Standard Model. The Higgs boson proved that the molasses is real, that the invisible field does fill the universe, shaping the weight of everything you see. But the Higgs is only part of the story. Other fields play their roles too, particularly in the dance of nuclear interactions. Consider the neutron, one of the building blocks of atoms. A neutron is not perfectly stable. Outside the nucleus, it decays after about 15 minutes, transforming into a proton, an electron, and a tiny ghostly neutrino. This transformation is guided by what we call the weak nuclear field, mediated by particles called W and Z bosons. It is through such transformations that the balance of matter in the universe takes shape. The weak force is responsible for processes in stars, for the burning of the sun, and even for the radioactive decay that warms the Earth's crust. In these interactions, something deeper is revealed, the role of symmetry. In physics, symmetry is more than beauty, it is a guiding principle. Emmy Noether, one of the most brilliant mathematicians of the 20th century, showed that for every symmetry in nature, there is a conservation law. Time symmetry leads to the conservation of energy. Space symmetry leads to conservation of momentum. The invariance of rotation leads to conservation of angular momentum. Hidden behind every reliable law of physics is a symmetry, like a secret spine holding up the world. You see this in everyday life too. The fact that the laws of physics work the same in New York as they do in Tokyo, or in your bedroom as they do on the moon, is a kind of symmetry. The stage does not favour one corner over another, and because of that symmetry, momentum and energy remain conserved. If reality played favourites, if the rules changed from place to place, the universe would be chaotic. Instead, symmetry gives order. The Higgs field itself is tied to broken symmetry. Once, in the earliest moments of the universe, particles may have all been massless, flying through space with equal footing. Then, as the universe cooled, the Higgs field crystallized into existence, breaking the symmetry and giving particles different masses. Some became heavy, some remained light, and the architecture of matter began to emerge. It was as though the stage floor, once flat and uniform, suddenly tilted, and the actors found themselves moving in new, differentiated ways. From this gentle breaking, the universe took on its familiar shape. To bring it closer, imagine a crowded room filled with people. A celebrity enters, and the crowd clusters around, slowing their passage. That person acquires an effective mass because of the interactions. Another, less recognized person can slip through with little resistance. This playful analogy was once offered to explain the Higgs mechanism. Particles gain mass through how they interact with the ever-present Higgs field, just as people gain resistance from how the crowd treats them. Mass may seem so ordinary. You feel it when you lift a book or climb stairs. But without the Higgs field, there would be no mass, no atoms binding, no stars burning, no planets forming. Reality would be a weightless sea of energy, with no stable structures to hold. The Higgs is the quiet, unseen reason that matter takes form, that apples fall, that you can rest in bed tonight without floating away into the void. And through Noether's insight, we see that mass, energy and motion are not arbitrary gifts. They are the consequences of deep symmetries, of hidden order written into the equations of nature. What looks like chaos, particles rushing, decaying, colliding, is in truth a kind of music, each note bound by symmetry, each beat conserving something precious. So when you think of mass, don't picture it as a simple number on a scale. Picture it as a relationship, born from the interaction between particles and the invisible Higgs field. And when you think of conservation laws, picture them as promises the universe keeps, thanks to symmetry, promises that make the world stable enough for stars, planets, and people to exist. Tonight, as you breathe, feel the weight of your body pressing against the bed. That weight is not just gravity holding you. It is the Higgs field granting substance to your atoms, the symmetry of space and time preserving your energy and momentum. In every breath, in every heartbeat, you carry the quiet gift of mass, a gift from the unseen field that holds reality steady. So far, our picture of reality has been graceful, almost musical. Fields providing the stage, particles as ripples, symmetry as the hidden order guiding every move. It might be tempting to think of the universe as perfectly balanced, like a flawless crystal or a mirror reflecting without blemish. But look closer, and you find that the mirror has cracks. Symmetry, for all its elegance, is not absolute, and in those tiny cracks lies one of the deepest mysteries of existence. Why anything exists at all. Consider matter and antimatter. According to the laws of physics, every particle has a mirror twin. The electron has the positron, the proton has the antiproton, the quark has the antiquark. These twins are identical in mass but opposite in charge. Bring a particle and its antiparticle together and they annihilate into pure energy, light flashing, mass disappearing. The early universe should have created matter and antimatter in equal measure. But if that had been the case, They would have cancelled each other out, leaving behind only empty radiation, no stars, no planets, no you. And yet, here you are. Somehow, matter gained the upper hand. Somehow, a tiny asymmetry tilted the balance, leaving a sliver of matter behind after most of the pairs annihilated. That sliver became galaxies, oceans, and apple trees. But how did this imbalance arise? The answer, or at least the hint of one, lies in broken symmetries called CP violation. C stands for charge, flipping particles into antiparticles. P stands for parity, flipping left and right like a mirror reflection. For a long time, physicists believed the laws of nature treated particles and antiparticles symmetrically, and that left and right were interchangeable. But experiments in the mid-20th century showed otherwise. Certain decays of subatomic particles like kaons and later B mesons revealed subtle biases. The universe does not treat left and right equally. The mirror image is not always a perfect match. You can imagine it like gloves. A left-handed glove and a right-handed glove are mirror images, yet they cannot be swapped. They are not truly identical. Nature, it turns out, has a preference, a handedness, a tiny tilt that favours one side. Neutrinos, those ghostly particles streaming through your body by the trillions, are always left-handed in their spin. Their mirror twin right-handed version does not seem to exist, at least not in the same way. Why nature plays favourites, no one fully knows. But this favouritism may be the key to why matter survived over antimatter. These cracks in symmetry are not just esoteric details, they are the reason you can sit here listening. If the universe were perfectly balanced, every atom of matter would have been cancelled by an atom of antimatter in the first fractions of a second after the Big Bang. The fact that matter lingers, that you can hold an apple, that stars burn in the night sky, is because reality itself contains small imperfections. Existence depends not on perfection, but on a symmetry. And perhaps that is a comforting thought. We often imagine perfection as the ideal, the highest state. But in the deepest physics, it is imperfection that allows the world to exist. A perfect balance would be empty. A flawless mirror would reflect but never create. It is the tiny cracks, the small biases, the subtle asymmetries that give rise to richness, diversity, and life. Even in everyday life you can feel this. Your left hand is not quite the same as your right. Your heartbeat is not perfectly regular, but varies slightly with each breath. Music itself would be dull if every note were identical, if every beat were evenly spaced. It is the variation, the asymmetry, that makes a song alive. The same, it seems, is true for the cosmos. Still, the puzzle remains unsolved. The amount of CP violation we've observed in experiments is not enough on its own to explain the vast dominance of matter over antimatter. There may be other cracks yet unseen, other hidden asymmetries waiting to be discovered. Physicists hunt for them in giant accelerators, in neutrino detectors buried deep underground, in the patterns of cosmic radiation left over from the Big Bang. Each experiment is like holding up another mirror, searching for the places where the reflection falters. And maybe this too tells us something about reality, that it is not a simple stage of rigid perfection, but a dynamic balance, leaning gently toward matter, toward existence, toward the possibility of beings who can ask these questions. If you are here, if anything is here, it is because the universe tips just slightly off-center. So tonight, as you rest, imagine the universe as a great hall of mirrors. Most reflections align, repeating endlessly, symmetry upon symmetry. But here and there, a crack runs through the glass. The reflections slip, the balance breaks, and through that tiny fracture, reality itself enters. You're here because the mirror was not perfect. You're the echo of an imperfection written into the laws of nature. And in that imperfection lies a strange kind of beauty. Because if the universe had been flawless, it would have been empty. Instead, it bent just enough to allow galaxies, stars, apples, and you. A world born from cracks in the mirror, where imperfection is the source of everything real. We've seen how fields and particles form the stage and actors of reality, how the Higgs field gives mass, and how tiny cracks in symmetry explain why matter exists at all. But physicists, restless and curious, are not satisfied with the stage that feels unfinished. The Standard Model, brilliant as it is, leaves questions unanswered. Gravity, for instance, the great shaper of space-time, sits awkwardly outside the framework, refusing to be woven into the same fabric as the other forces. And so begins one of the grandest quests in science, the search for unity. The hope that all the forces and particles, all the ripples and symmetries, might be described by a single, elegant theory. It is a quest full of ambition, but also full of suspicion, because the answers we've glimpsed so far seem both beautiful and strange. One idea is supersymmetry, often called SUSY for short. In the Standard Model, every particle belongs to a certain family, fermions like electrons and quarks, which make up matter, and bosons like photons and gluons, which carry forces. Supersymmetry proposes that every particle has a secret twin in the other, family. Each fermion would have a boson partner, and each boson would have a fermion partner. These superpartners could help explain puzzles like the nature of dark matter, the mysterious substance outweighing ordinary matter in the cosmos. If SUSY is real, then the universe is far more crowded with actors than we currently see, an unseen cast waiting in the wings. But so far, despite years of searching in powerful accelerators, no clear evidence of supersymmetry has appeared. The stage remains quiet. Physicists wonder, are the superpartners hiding at energies beyond our reach? Or is supersymmetry a dream that reality simply does not share? Another bold vision comes from string theory. Instead of particles being point-like, tiny marbles without size, string theory imagines them as minuscule vibrating strings. Each mode of vibration corresponds to a different particle, like guitar strings plucked into various notes. One vibration produces an electron, another a photon, another a quark. Even gravity emerges naturally, as a special vibration of the string. In this vision, the universe is not built from particles but from music, an endless symphony played on cosmic strings. But strings demand extra space, not just the 3 dimensions we know, but 10 or 11 dimensions curled up so tightly we cannot see them. Imagine a garden hose viewed from far away. It looks like a one-dimensional line, but up close, you see its roundness, its hidden dimension curled around. String theory suggests our universe may hide dimensions like that, curled, compact, unseen, but essential for the cosmic music to play. Still, string theory, for all its elegance, has not yet offered testable predictions we can confirm in experiments. It remains a mathematical symphony, beautiful on paper, waiting for reality's applause or its silence. And then there is loop quantum gravity, another attempt to bring gravity into the quantum fold. Instead of strings, it imagines space itself as woven from tiny loops, discrete units of geometry, like a fabric made from individual threads. Space is not smooth and continuous but grainy, with the smallest possible chunks of area and volume. Time itself may tick in discrete steps, like frames in a cosmic film. If true, then reality is pixelated at its deepest level, woven from loops so small we cannot yet resolve them. All these attempts, SUSY, strings, loops, are ambitious. Each offers a vision of unity. Each strives to answer why the universe is as it is. Yet each also carries uncertainty, suspicion, the possibility that we're chasing shadows. It is a humbling reminder that even with centuries of progress, even with equations that predict to 12 decimal places, we're still in the middle of the mystery. The Standard Model works astonishingly well, But it is not the final story. We do not yet know how to write the book that includes both quantum fields and gravity, both the ripples of particles and the curves of space-time. But maybe that too is part of the wonder. Imagine sitting in a theatre just before the curtain rises. You know the actors, you know some of the lines, but you also sense there is more, a hidden script, a deeper play about to begin. That is where physics finds itself. The standard model is the rehearsal, the first act. The full performance is still waiting. So as you lie here, imagine the universe as an orchestra tuning up. Supersymmetry suggests more instruments than we can currently hear. String theory suggests that all the instruments are strings vibrating in hidden harmonies. Loop quantum gravity suggests that the very hall itself, the space in which the music plays, is woven from tiny loops of sound. We do not yet know which melody is true, but we know that reality is still playing, still unfolding its hidden score. And perhaps the lesson, as always, is not certainty, but humility. Reality is larger than our theories. It may be strings or loops, symmetries or broken mirrors. It may be something we have not yet imagined. What we can say, gently, is that the search for unity is itself part of reality, the human desire to see wholeness, to weave all the fragments into a single, graceful pattern. When physicists dream of unifying the forces, of bringing quantum mechanics and gravity together on the same page, one strange clue keeps appearing. A whisper that our universe might not be what it seems. The clue is holography, the idea that the three-dimensional world we move through could be, in some sense, a projection from a deeper two-dimensional reality. It sounds like science fiction, and yet it arises naturally from the mathematics of quantum theory and gravity. To imagine this, think of a hologram on a credit card. Tilt it in the light, and you see a three-dimensional image rise from a flat surface. The depth is an illusion, encoded in the interference of light. In the same way, some physicists propose that our universe may be like a cosmic hologram. All the information describing our three-dimensional reality might be stored on a two-dimensional boundary, like a film projecting a 3D movie. This strange idea gained traction through work on black holes. Black holes are paradox machines, places where gravity crushes matter so fiercely that not even light can escape. According to Einstein's relativity, once something falls past the event horizon, the invisible boundary, its information should be lost forever. But quantum mechanics insists that information can never truly vanish. This clash between the two pillars of physics is called the black hole information paradox, and it has puzzled scientists for decades. The solution, or at least the hint of one, came from holography. In the 1970s, Jacob Bekenstein and Stephen Hawking discovered that black holes are not completely black. They emit a faint radiation, now called Hawking radiation, and they have an entropy proportional not to their volume but to the area of their surface. It was a startling result. The amount of information a black hole can contain depends on its surface area, not what lies inside. It was as though the entire story of what falls in could be written on the horizon itself, like a cosmic diary inscribed on the skin of the black hole. From this grew the holographic principle, the idea that all the information within a region of space can be described by information encoded on its boundary. Just as a hologram on a flat card contains the recipe for a 3D image, the universe may contain its own information on a cosmic surface we cannot directly see. This principle took a sharper form in the late 1990s when physicist Juan Maldacena proposed what is now called the AD-CFT correspondence. In this duality, a universe with gravity and a certain kind of space, anti-de Sitter space, is mathematically equivalent to a universe without gravity living on its lower dimensional boundary, described by a conformal field theory. It was as if two entirely different plays, one a grand drama of curved space-time, the other a simple stage of quantum fields, turned out to be telling the same story. Two descriptions, one reality. Although our universe is not anti-de Sitter space, the principle offers tantalizing hope. If holography can work there, perhaps it points to a way of reconciling gravity and quantum mechanics more generally. Perhaps the fabric of space-time itself is not fundamental, but emerges from deeper layers of information encoded on boundaries. Reality, in this view, is less like solid stone and more like a projection, a shadow cast from a hidden source. This sounds unsettling, as if we were characters in a cosmic cinema, our lives unfolding on a screen we cannot see. But pause for a moment and consider, even if the world is a hologram, it is still your world. The apple you bite, the laughter you share, the breath you take, they are as real as any projection can be. A movie can make you laugh and cry, can change your heart, even though its images are made of light on a screen. So too, if reality is holographic, its authenticity is not diminished. It is simply revealed as deeper, stranger, and more wondrous than we thought. Black holes remain the great keepers of this mystery. They are paradox engines, places where our theories collide. Some physicists describe them as cosmic hard drives, storing the information of everything that falls in, encoded somehow on their event horizons. Others think the holographic principle might extend to the universe itself, making reality at large a kind of projection from a hidden surface. We don't yet know, but the hints keep pointing in this direction. To bring this closer, think of a cinema. You sit in a theatre, immersed in a story. The characters live in 3 dimensions, move, love, struggle. Yet behind it all is a flat reel of film, or in modern times, a digital code. The story is real to you, even though it arises from something simpler, a universe. Maybe the same, a vivid 3-dimensional story arising from a deeper layer of encoded information. And perhaps there is something comforting in this possibility. If reality is a hologram, it means the world is more deeply connected than we imagined. Boundaries carry the story of what lies within. Surfaces remember. Nothing is ever truly lost, only written in a different language, on a different canvas. So tonight, as you rest, picture yourself in a quiet theatre. The lights dim, the screen flickers, and suddenly a world appears. Mountains, rivers, stars. You lean back, immersed, forgetting the projector behind you. That is what living in a holographic universe might feel like. Not a deception, but an immersion. Not a trick, but a revelation. And even if it is a projection, it is still real. Because it is the only story you have, the only world you know, projected or not. We've spoken of fields, particles, and the subtle cracks in symmetry. We've seen how black holes hint at holograms, and how physicists chase unity in strings and loops. But beneath all this, there lingers a quieter puzzle. How does time itself really work? We live as if time flows forward, moment by moment, from past to present to future. Yet physics, with its equations written in elegant symmetry, suggests that past and future may be more entangled than we imagine. Perhaps time is not a one-way current at all, but a tapestry woven from both ends. One of the gentlest and strangest interpretations of quantum mechanics is called the transactional interpretation. It suggests that when a particle moves or a quantum event occurs, waves are exchanged not only forward in time but also backward. A particle emitting a photon, for example, sends out an offer wave into the future. A potential absorber, say, an electron waiting somewhere down the line, sends back a confirmation wave into the past. The two meet in a kind of handshake across time, sealing the transaction. The event we observe is not simply pushed forward by causes behind it, but also pulled into place by outcomes ahead. It is a radical idea, yet strangely soothing. It paints the universe not as a blind march forward, but as a conversation between what has happened and what will happen. Like two dancers reaching toward each other, meeting hands in the middle, past and future complete the step together. This idea brushes against another broader vision, the block universe, In this picture, time does not truly flow. Instead, the past, present, and future all exist at once, like a vast four-dimensional block of space-time. Your birth, your listening to this story, and your final day are all laid out in the tapestry, equally real. The sense of flowing time, of a moving present, is not a property of the universe but of our perception. We are like readers moving line by line through a novel, while the whole story already exists between the covers. Some philosophers, however, prefer the growing block universe. In their view, the past and present are real, but the future is not yet woven. The block grows as each new moment crystallizes, like stitches added row by row to a scarf. The present, in this picture, is where the needles are working, weaving fresh reality into the fabric, while the future remains an unwoven skein of yarn. Both views are compelling, and both carry a kind of poetry. The block universe offers the comfort of permanence. Every joy, every love, every laughter is eternally inscribed. The growing block offers the comfort of possibility, the idea that the future is still open, not yet decided, waiting to be shaped. Physics itself leans curiously toward the block. Einstein once wrote to a grieving friend that for those who believe in relativity, the distinction between past, present, and future is only a stubborn illusion. The equations of relativity and quantum mechanics do not distinguish between forward and backward. They work just as well in either direction. Time's arrow, the sense of before and after, emerges not from the laws but from conditions, like entropy increasing, ice melting, stars burning. Yet, in our lived experience, the growing block feels closer. You cannot yet taste tomorrow's bread. You cannot recall laughter that has not yet happened. To you, the present feels alive, and the future feels unwritten. The warmth of the oven is here, now, while the loaf is still rising, its shape uncertain until the baking is done. Perhaps the truth, as often in physics, is that both pictures hold some element of reality. The universe may indeed be a timeless structure, with all events laid out. And yet, within that structure, consciousness may be the needle, weaving our path row by row, giving us the gift of experiencing the block as a flow. We may be both eternal and momentary, fixed in space-time and also passing through it. To bring this closer, think of weaving fabric. Each row of threads is laid down, locked into place. Look back, and you see the rows already woven, solid and real. Look ahead, and you see the loom waiting, the yarn unspooled, the pattern unwritten. The block is the finished cloth. The growing block is the weaving in progress. Both are true, depending on where you stand. And perhaps the transactional interpretation is another layer to this weaving, where not only the past lays down rows, but the future reaches back to guide the pattern, tugging gently on the threads. So, as you drift tonight, imagine your life as a tapestry. The rows behind you are firm, filled with memories. The row beneath your fingers is the present, bright and vivid. The rows ahead are threads not yet drawn, waiting to be woven. Whether the cloth already exists in its entirety, or whether it grows with each passing breath may not matter. What matters is that the weaving is beautiful, and that you are part of it. We speak so casually of now. You are listening now. You are lying in bed now. Outside, the night or the day is happening now. It feels like the most obvious concept in the world, that there is a single present moment, shared by everyone and everything, like a spotlight sweeping across the stage of time. But the closer we look, the more this spotlight dissolves. Physics says now is slippery, subjective, different for each observer. Philosophy argues whether it exists at all. And we, caught between equations and experience, must ask, where does now truly live? In relativity, the answer is unsettling. There is no universal clock, no master rhythm ticking for all. Two observers moving differently will disagree on whether events happen at the same time. What you call now might be part of the future or past for someone racing past you. The universe does not offer a single slice labelled present. It offers many overlapping slices, each tied to an observer's motion and position. Time is local, not global. Imagine standing in your kitchen, watching bread rise in the oven. The dough swells slowly, its surface cracking, its scent filling the room. This feels like the present, immediate, undeniable. But think of someone on a distant planet circling another star. Their present is not your present. Even the signals of your existence, light, radio waves, whispers of gravity, take years to reach them. For them, your now is already there then, and your now is filled with light from stars that died long before humans walked the earth. What feels immediate is already a patchwork of past stitched together into your present. Philosophers have long wrestled with this. Presentism argues that only the present moment is real. The past has slipped away. The future does not yet exist, and only this instant has true being. Eternalism, on the other hand, claims that past, present and future are all equally real. Your childhood, this moment, and your future old age all exist within the fabric of space-time, like pages in a book. You may read them one by one, but the book is already complete. Both views have their comfort. Presentism gives weight to the immediacy of experience, the warmth of bread as you touch it, the laughter of a friend beside you, the feel of breath in your lungs. Eternalism gives weight to permanence, every memory, every joy, every sorrow preserved eternally in the block of space-time. Neither is easy to let go, and yet, perhaps, now is not something the universe defines, but something we do. The physicist Sean Carroll once wrote that the present moment is not carved into space-time but constructed by our minds. Consciousness knits together sensations, memories and expectations into a bubble we call the present. The smell of bread in the oven combines with the memory of placing it there and the anticipation of tasting it soon. Past, present and future converge in your awareness, and you call it now. In this sense, now is like the crest of a wave. The wave contains water that has flowed from behind and water that will move ahead. But to you, standing on the shore, the crest is the moment that exists, shimmering and immediate. Consciousness rides the crest, always moving, always weaving a new present from threads of past and hints of future. This does not mean now is an illusion. It means now is local, personal, stitched together in each observer's mind. You live in your own present, woven from your path through space-time, your memories, your expectations. Others live in theirs, and sometimes those presents align when you share a meal, a conversation, a laugh. But beneath the alignment, each of you carries your own clock, your own spotlight, your own crest of the wave. There is beauty in this relativity of time. It means the universe is not a rigid machine forcing every being into the same rhythm. It is a symphony of tempos, each instrument playing its own pace, harmonizing in moments, diverging in others. Your present may not be another's, but together they form a richer music than a single beat could provide. So where does now live? It lives in you. It lives in the loaf swelling in the oven, in the warmth of your blanket, in the slow pulse of your breath. It lives in the weaving of memory and anticipation into the tapestry of awareness. The universe may not grant a universal present, but it grants each of us our own moment, our own experience of time's gentle flow. And perhaps that is enough, because whether or not now exists for the universe, it exists for you. It is the stage on which you live, the crest on which you ride, the bread you smell, the heartbeat you feel. In the grand, indifferent cosmos, now is your gift, your anchor, your home. So far, our journey through reality has taken us deep into atoms, fields, and the fabric of space-time itself. But there is one frontier we cannot ignore. perhaps the most intimate and mysterious of all. Because what does it mean to say something is real if we can't account for the reality of our own minds? The story of consciousness, of the self that listens to these words, is as puzzling as black holes or quantum fields. And yet, unlike black holes, you experience it directly, every waking moment. Philosophers have long puzzled over identity. What makes you you and not someone else? One famous thought experiment is called the ship of Theseus. Imagine a wooden ship preserved in a harbour for centuries. Over time, every plank rots and is replaced. Eventually, none of the original wood remains. Is it still the same ship? And if someone gathered all the discarded planks and rebuilt them elsewhere, which would be the real ship? Now, consider your own body. Every 7 to 10 years, almost every atom in you is replaced. The cells in your skin, your blood, even many in your bones are renewed. You're not made of the same material you were a decade ago. And yet, you still call yourself you. So what then is your identity? Not the atoms, because those are swapped. Not the planks of the ship, because they can be replaced. Identity seems to rest in something less tangible, perhaps in the pattern, the continuity, the story held together across time. And nowhere is this truer than in the brain. Your brain is a network of about 86 billion neurons, each a cell that communicates with thousands of others through tiny electrical pulses. The brain is not fixed either. It changes constantly, rewiring with each experience, strengthening some connections, weakening others. Neurons die, new ones are born, pathways shift. Yet somehow across this changing landscape, there persists a sense of I. This is what scientists mean when they speak of emergence. Consciousness may not be a single spark hidden in the brain, but an emergent property of countless simple interactions, like a pattern appearing in a mosaic. No single tile makes the picture, but together they form an image. No single neuron is the mind, but together, in vast dynamic networks, they give rise to thought, memory, sensation. Think of a murmuration of starlings, thousands of birds wheeling in the sky, creating shapes that move as one. Each bird follows only simple rules: stay close, don't collide, match the motion of neighbours. Yet from these rules emerges a fluid, shifting pattern that seems alive in itself. Consciousness may be similar. Billions of neurons, each obeying simple rules, giving rise to the great flock of awareness, the self that says, I am. Or consider music. A single note on a piano is simple, clear. But place many notes together, in harmony and rhythm, and something emerges that is more than the sum of its parts. A melody, a song, an emotion. Consciousness too might be a kind of music, emerging from neurons firing in patterns, weaving sensations into the song of experience. This does not mean that the self is an illusion in the sense of being false. It means the self is a construct, a story, a continuity weaves itself from the changing planks of the ship. You're not the atoms of your body. You're the pattern they form. You're not the neurons of your brain. You're the music they play. And that music persists even as the players change. Think of memory. The child you once were, sitting in a classroom, tasting your first apple, learning your first word. That child's atoms are gone, their neurons replaced. But the memory remains, carried forward in the evolving network, re-encoded many times. Continuity, not permanence, makes you who you are. And this raises profound questions. If your self is a pattern, not a material, could it in principle be replicated elsewhere? Could consciousness arise in another medium, like a machine? Could the music of thought be played on a different instrument? These are questions for later sessions, but already the ship of Theseus analogy hints at them. If identity is a pattern, then what matters is not the planks, but the arrangement. Yet, even if the self is a story, that story is powerful. It is the anchor of your life, the voice that listens now, the awareness that drifts towards sleep. Whether consciousness emerges from neurons or hides in some deeper layer of reality, it is real to you. It is as immediate as the scent of bread, as vivid as the colour red. So tonight, as you lie still, consider yourself as the ship of Theseus. Your atoms are not the same as before, your brain is not the same as yesterday's. But the pattern endures, weaving continuity across change. You are the ship that thinks itself, the melody carried across instruments, the murmuration moving as one. And that may be the most remarkable truth of all. That matter, when arranged just so, can wonder about itself. The cathedral of atoms gives rise to thought. The ocean of fields gives rise to awareness. And here you are, a ripple in the universe, reflecting on what it means to be real. We've pictured the self as the ship of Theseus, changing planks, shifting neurons, yet a pattern that endures. But even with emergence and networks of billions of cells, a deeper question remains. What is consciousness itself? How does matter give rise to experience? The redness of an apple, the warmth of a blanket, the ache of longing, the joy of laughter. This is the hard problem of consciousness, and it sits at the very edge of what we know. One proposal, ancient and modern at once, is panpsychism. The idea that consciousness is not unique to humans or even to brains, but is a fundamental property of matter. In this view, everything has some tiny spark of experience. Not that rocks think or atoms dream, but that at some level, awareness is woven into the fabric of existence, just as mass and charge are. A grain of sand, a quark, a leaf on a tree, all may carry a glimmer of inner life, unimaginably faint, combining into the rich consciousness we know. Many scientists find this idea unsettling, perhaps too mystical. Yet it offers a way to explain why consciousness exists at all, because it never had to emerge from nothing. It was always there, waiting, growing more complex as matter arranged itself into brains. Like faint sparks combining into a fire, panpsychism suggests awareness scales with complexity. Another frontier is artificial intelligence. Could a machine ever be conscious? Could silicon circuits, arranged just right, give rise to awareness as neurons do? If the mind is a pattern, not a substance, then perhaps yes. A different instrument could play the same music. Already, we build machines that imitate conversation, recognize faces, generate art. But are they aware, or are they only echoing without inner light? That question lingers, and perhaps will linger for a long time. One of the most prominent modern theories is integrated information theory, or IIT, proposed by neuroscientist Giulio Tononi. It suggests that consciousness is the integration of information, how much a system's parts communicate with and depend on one another. A simple system, like a light switch, carries almost no integrated information. A human brain with billions of neurons cross-talking in intricate loops carries an immense amount. IIT even assigns a measure called phi to quantify the level of consciousness. The more integrated the information, the richer the awareness. To bring this closer, think of a smartphone. On its own, each part is simple: the screen, the battery, the processor. But when connected, when circuits flow together, the phone lights up, becoming something more than the sum of its parts. It does not yet have consciousness, but the analogy helps. When information integrates across a system, new properties emerge. In us, that property is the spark of experience. Still, questions remain. Does IIT capture what it feels like to taste chocolate, to remember a song, to wonder about time? Or does it only measure structure, leaving out the mystery of subjectivity? Can consciousness ever be reduced to numbers, or is it something forever beyond equations? Whatever the answer, one thing seems clear. Consciousness is deeply tied to information. The brain is not a static thing, but a flow of signals, patterns of firing, rhythms of oscillations. Your sense of self at this very moment is the integration of memory, sensation, and expectation into a single unified experience. The neurons, like musicians, play together in sync, and from their harmony rises the music of awareness. This idea that mind is information brings us back to the wider universe. Earlier we saw John Wheeler's proposal, it from bit, the idea that physical reality arises from informational yes-no choices at the most fundamental level. If matter is information and consciousness is integrated information, then perhaps the divide between physics and mind is not as wide as it seems. Perhaps both are patterns in the same informational fabric. Pause for a moment and feel your breath, the rise and fall of your chest, the warmth of the air as it enters, the faint rhythm of your heartbeat. Each of these sensations is information, nerve signals travelling to the brain, integrated into a unified sense of being alive. You are an informational pattern reflecting on patterns, a ripple of awareness considering itself. At the edge of consciousness, questions multiply. Could awareness survive beyond the body if the pattern were preserved elsewhere? Could machines cross the threshold into genuine experience? Is consciousness fundamental or emergent or both? We do not yet know, but perhaps that not knowing is part of its beauty. Consciousness is not just a problem to be solved, but an experience to be lived. So as you rest tonight, imagine yourself as a constellation of information, each neuron a star, each connection a thread of light, weaving together into the galaxy of your mind. You are the ship of Theseus, yes, but you're also the orchestra, the murmuration, the constellation, and at the centre of it all glows a light we call awareness, fragile, profound, and endlessly mysterious. So far we've wandered through atoms and fields, through the cracks in symmetry and the hints of holograms. We've considered time as a tapestry, consciousness as a pattern. But there is an even more radical idea waiting in the wings, that beneath matter, beneath energy, beneath even space and time, lies something even simpler. Information. John Archibald Wheeler, one of the great physicists of the 20th century, captured it in a phrase, it from bit. By this he meant that everything we call real, the it, arises from yes or no questions, the bit. Reality at its core might not be particles or waves, but binary choices like the switches inside a computer. Each atom, each photon, each star might be the visible surface of a vast informational sea. This is not as abstract as it sounds. Think of a photograph on your phone. To your eye, it is a smooth image, faces, landscapes, colours. But behind it all is a lattice of pixels, each one coded by numbers. The photograph is information made visible. In the same way, Wheeler suggested, the universe itself might be the image, while information is the pixels hidden underneath. One way to picture it is to imagine the universe asking and answering questions. Is the electron spin up or down? Yes or no? Did the photon go left or right? Yes or no? Every quantum event is like a coin toss that resolves into a clear result. From these endless questions and answers, the world unfolds. Reality is the grand accumulation of choices, of bits. This idea naturally leads to an even bolder speculation, the simulation hypothesis. Nick Bostrom, a philosopher at Oxford, proposed that if advanced civilizations could create simulated worlds indistinguishable from reality, then the odds suggest we ourselves might already be living in one. After all, if even one civilization created billions of simulations, there would be far more simulated realities than real ones. Statistically then, we might be inside one. At first this sounds unsettling, like the plot of a science fiction film. Are we characters in someone else's video game, unaware of the console humming outside our world? But pause and notice. Even if we were, would it matter? The apple you bite still tastes sweet. The laughter you share still warms you. The stars still shine overhead. Whether projected from code or built from quarks, the experience remains your own. Everyday life gives us gentle ways to grasp this. Think of a video game character running across a digital landscape. To the character, the ground feels solid, the sky stretches overhead, mountains rise in the distance. They do not know they are made of code, of pixels flickering on a screen. Yet their world has rules, patterns, structures that hold steady. In our own lives, we too live in a rule-bound world. Physics is our code, mathematics our source. Whether that code is real or simulated hardly changes the experience of living within it, and perhaps there is a comfort in this perspective. If reality is information, then nothing is ever truly lost. Just as data can be stored, copied, transformed, perhaps the universe preserves its story in ways we cannot see. Information is durable. It may survive even when matter changes form. The burning of a book destroys its paper, but not the words if they are copied elsewhere. In physics, too, information has a strange resilience, whispering that nothing is ever completely erased. The simulation hypothesis, too, need not be bleak. Instead, it can inspire wonder. If we're living in a simulation, then we are part of a grand experiment, an artwork crafted beyond comprehension. And if we're not, then our universe is even more remarkable. A natural system that mimics the qualities of code and logic. Either way, reality is astonishing. Think of your own life for a moment. Every conversation you've had, every dream you've dreamed, every sound you've heard, each is information, flowing through neurons encoded in memory, shaping who you are. You're already an information system, a constellation of bits woven into a narrative. The universe, at its largest, may not be so different. Wheeler once said that we live in a participatory universe. By observing, by asking questions, we bring reality into being. Like participants in a conversation, we help shape the story by the very act of listening. The world is not a stage set in stone, but an unfolding dialogue, written in the language of information. So tonight, as you lie here, imagine the universe as a great library of choices. Each star, each atom, each breath is a letter, a bit, a yes or no inscribed in the book of reality. You're part of that library, both a reader and a page, both the observer and the observed. Whether you call it physics or simulation or information, the story is the same. Reality is written bit by bit, choice by choice, moment by moment. And in that story, your experience is real enough. Whether projected or primordial, the apple still crunches, the night still falls, your heart still beats. You live in a world of information, but to you, it is simply life. We've just wandered through Wheeler's It from Bit, and the suggestion that reality may be woven from information itself. But some thinkers go further still. What if information is only the middle layer? What if, beneath even that, the universe is mathematics? Pure, abstract, timeless mathematics. This is the bold idea of Max Tegmark, a cosmologist at MIT, who argues that mathematics does not merely describe reality, but is reality. In his mathematical universe hypothesis, every structure that can exist mathematically also exists physically, somewhere in the vast multiverse. Our universe, with its galaxies and stars and people, is one such structure, an intricate solution to the equations of math. At first this sounds dizzying. Surely mathematics is just a language we humans invented to describe the world. 2 apples plus 2 apples equal 4 apples because we made up numbers to keep track. But the deeper you go, the more uncanny mathematics becomes. Electrons obey equations perfectly, never deviating. The orbits of planets, the bending of light, the ripples of gravitational waves, all follow mathematical laws as if the universe were reading from a script. Math does not merely approximate reality. It seems to be its fabric. Consider music. At its surface it is sound, vibrations in the air, melodies in the ear. But at its root, music is mathematics. The notes on a piano follow ratios of frequency. Harmonies arise from numerical relationships. Rhythms are divisions of time. Yet music is not lifeless arithmetic. It is moving, emotional, real. You can live inside music, even if it is built from ratios. Perhaps reality itself is the same. We live inside equations, experiencing them not as numbers, but as apples, sunsets, laughter, and love. This view is both comfort and unease. If the universe is mathematics, then it is timeless. Equations do not fade. The Pythagorean theorem was true long before humans discovered it, and it will remain true long after we're gone. In the same way, the mathematical structure of our universe may exist outside of time, eternal. That means your life, every moment of it, may also be etched into that timeless structure, preserved forever in equations. But it also means that our universe is not unique. If every mathematical structure exists, then there are countless universes, each as real as ours, built from different equations. Somewhere, perhaps, is a universe with different forces, different constants, different rules of physics altogether. Somewhere else may lie universes with no matter at all, only pure geometric forms. Reality, in this view, is not one universe but the entire landscape of mathematics. To bring this closer, think of geometry class. You may remember drawing triangles, circles, cubes. Each shape is defined by simple mathematical rules. In Tegmark's vision, each of those shapes could correspond to a kind of universe, some simple, some unimaginably complex. Ours is simply one of the more intricate solutions, rich enough to contain galaxies, atoms and minds pondering their own equations, and in some sense this perspective feels natural. When you look at the night sky, the motions of planets and stars follow precise, predictable patterns. When you listen to a symphony, the notes and rhythms align in ratios that echo mathematics. Even your own heartbeat follows rhythms, cycles, waves. Everywhere you look, the language of math quietly whispers in the background. This does not mean we must picture the universe as sterile or lifeless. Just as music transcends the sheet of notes, so too does reality transcend the equations. The notes become melody, the math becomes experience. The apple is not numbers to you, it is sweetness, crunch, nourishment. The math is the foundation, but the lived reality is the story built upon it. And maybe there is a quiet comfort in this vision. If reality is mathematics, then it is not fragile. It does not depend on a stage that could collapse, or a simulation that could be turned off. It exists timelessly, as patterns that cannot be erased. You are part of that pattern, a living equation that thinks, feels, and dreams. So tonight, imagine yourself as a melody in an eternal song. The music is mathematics, but the experience is your life. Notes that rise and fall, harmonies that weave together, pauses and crescendos that shape your story. The universe may be an equation, but you are the music it plays. And that music is as real, as moving, and as precious as anything could ever be. We have imagined reality as particles, fields, information, and even equations. But whatever its true nature, there is another question that hangs quietly at the edge of thought. How will it all end? The universe has been unfolding for 13.8 billion years, galaxies drifting apart, stars igniting and fading, structures forming and dissolving. Where does this long story lead? If reality is a play, what is its final act? One answer comes from the second law of thermodynamics, the law of entropy. Entropy is the measure of disorder, of energy spreading out. An ice cube melts, the coldness disperses into the drink, and the process cannot reverse itself. A candle burns, releasing heat and light that scatter outward, never to be fully gathered again. Every process leaves behind a trail of increasing entropy, a one-way arrow that gives time its direction. Now extend this to the entire cosmos. Stars burn their fuel, galaxies scatter, black holes slowly evaporate. Over unimaginable spans of time, entropy increases everywhere until the universe reaches what physicists call heat death. It is a misleading name because in truth it is the absence of heat, the absence of difference, a state where everything is spread so evenly that no work can be done, no flame can burn, no star can shine. Picture a vast soup, thin and dark, where every particle is so evenly distributed that nothing distinguishes one place from another. The cosmos has not ended, it still exists, but it has gone quiet. Energy is still present, but too diffuse to kindle anything new. It is as though the great fire of the universe has burned down to ash, leaving behind only a lukewarm shadow. It is a haunting image, but also strangely peaceful. Imagine a candle burning in a silent room. At first the flame dances, flickering, filling the air with light. Then slowly it gutters, shrinks, and finally goes out. The room remains, but it is quiet, still, dark. The universe, in its heat death, may resemble that silent room, an existence without drama, without change. Of course, this future lies so far beyond us that the numbers themselves feel surreal. Stars like our sun will last for billions more years. Even after the last star fades, black holes will endure for incomprehensible spans of time, slowly evaporating through Hawking radiation. The timescales stretch beyond imagination. Google years, 100 years, numbers so vast that the mind cannot truly hold them. For all practical purposes, heat death is eternity away, and yet it is worth reflecting on, because it tells us something about reality here and now. The arrow of time, the flow from order to disorder, is why we live in a dynamic universe. We exist in a window of history where stars still burn, where matter still clumps, where life can emerge. This is the era of drama, of stories, of change. It is a brief spark in the cosmic timeline, a flame in the quiet room. Perhaps this makes our present all the more precious. You are alive in a universe that is still warm, still active, still filled with light. The galaxies have not yet drifted too far, the stars have not yet gone dark. We exist in a fleeting chapter, a rare balance between the uniformity of the early universe and the uniformity of the distant future. It is a fragile window, and we happen to live within it. Think of a sunset. The light glows rich and colourful for a brief time between the harsh brightness of day and the deep black of night. That moment of beauty exists only in transition. In the same way, we may be living in the sunset of the universe, a time when things are changing, glowing, beautiful, before the long night descends. And perhaps heat death, for all its silence, is not an end to mourn, but a horizon to accept. The universe will not vanish. It will not cease. It will become a place of stillness, a calm sea of evenly spread energy. Reality will remain, but in its quietest form. So as you rest tonight, imagine the cosmos stretched into the far future. Stars fading, galaxies scattering, black holes whispering away, and then silence, darkness, a thin soup of particles drifting without urgency. A candle extinguished, a room at peace. It is haunting, yes, but also serene. For in that final stillness, the story of everything finds its horizon. Not a violent end, but a quiet one. The vision of heat death paints a universe stretched thin, quiet and still, with entropy maximized and energy spread evenly across the cosmic sea. But in physics, even in such stillness, fluctuations can occur, tiny, rare disturbances in the otherwise uniform soup. Most of these fluctuations would be trivial, like a few particles gathering briefly before dispersing. But over unimaginably vast timescales, stranger fluctuations become possible, and among them lies one of the most haunting and mischievous ideas in science, the Boltzmann brain. The name comes from Ludwig Boltzmann, a 19th century physicist who helped pioneer our understanding of entropy. He proposed that the universe itself might be the result of a gigantic fluctuation, a rare event in which order arises from chaos. Later thinkers pushed this idea to its unsettling extreme. If fluctuations can create anything, then given enough time, they could create a single conscious brain, complete with false memories and sensations drifting for an instant in the void. A mind born whole, remembering a life it never lived, vanishing again before it could understand itself. It sounds absurd, almost comical, and yet it is a logical consequence of thermodynamics applied to eternity. If the universe lasts long enough, then in principle, random configurations of particles could assemble into any structure, including something as elaborate as a brain. And because it is vastly easier to fluctuate into one brain than into an entire universe of galaxies and stars, the unsettling conclusion is that Boltzmann brains might be more probable than beings like us. This leads to a radical kind of skepticism. How do you know you're not a Boltzmann brain right now? Your memories of childhood, of walking in sunlight, of hearing your name, all could be false imprints, assembled in an instant. The apple you think you tasted, the conversations you recall, even the sense of lying here listening to this, all could be the flicker of a fluctuation, lasting just long enough for you to wonder before dissolving back into nothing. Of course, most physicists treat this idea with caution, even humour. The very fact that we observe a vast structured universe full of galaxies suggests that we are not fleeting fluctuations. Reality seems to be much more than a brain's brief hallucination. Still, the possibility is a reminder of how strange and fragile our assumptions can be. To bring this closer, imagine dreaming. In a dream, you feel certain of the world around you. You taste, touch, see, and feel until the moment you wake and realize none of it was real. The Boltzmann brain scenario suggests that waking itself might be impossible, that the dream of reality could itself be a fluctuation. Or think of a movie character. Within the story, their memories and experiences are real to them. They believe in their world. They never realize they are lines of code, flickers of light on a screen. The Boltzmann brain raises the mischievous question, what if we too are characters in such a moment, unaware of the fleeting nature of our stage? Yet even if that were true, what would it change? If your memories are illusions, they still feel real. If your sensations are momentary, they still move you. A dream can still bring joy. A story can still bring tears, even if it is not lasting. Reality, whether cosmic or fleeting, is still lived. There is a gentle humour in this thought. If you're a Boltzmann brain formed spontaneously in the void, then at least you get to enjoy the illusion of listening to this story, drifting toward rest. And if you are not, then you live in a vast universe with galaxies, stars, and a long cosmic history. Either way, your experience is valid, your life real to you. Physicists sometimes joke, if you are a Boltzmann brain, good night anyway, and perhaps that is the most reassuring conclusion. Whether the universe is a grand unfolding or a fleeting fluctuation, your moment of experience is yours. The bread still smells warm in your memory. The laughter of a friend still echoes in your mind. The stars still shine, whether for billions of years or a single second. So as you close your eyes tonight, imagine the vast, quiet universe, stretched into its heat death, particles drifting like dust in an endless void, and somewhere, improbably, a brain flickers into existence, complete with the memory of listening to this story. Perhaps it is you, perhaps it is not, but either way, the moment is real enough to carry you into sleep. And if you are a Boltzmann brain, then let this be your lullaby, gentle, fleeting, and enough. We began this long journey with something simple, an apple in your hand. We sliced it, peeled back its layers, found cells, molecules, atoms, quarks, and perhaps even strings or bits of information humming below. We asked whether the apple was matter, wave, probability, or projection. We followed reality into fields, symmetries, cracks in mirrors, handshakes across time, and the mysteries of consciousness. We stretched the future to its quiet horizon, and even dared to wonder whether we were only fleeting Boltzmann brains. And now, at the end, it feels right to return to that apple, whole, solid, ordinary, waiting to be bitten. Because whatever reality may be at its deepest level, you live it not in equations, but in moments. You live it in the sweetness of fruit, in the warmth of a blanket, in the sound of a friend's voice. Physics can reveal dazzling truths, but your everyday experience is where reality finds its home. Take the apple once more in your mind's hand. It is real enough for you to taste, to nourish you, to remind you of orchards and seasons. Even if, as Wheeler said, it is built from bits, or as Tegmark said, it is mathematics come alive, or as Bostrom said, it is a simulation, it is still an apple to you. The crunch is real. The flavour is real. The moment is real. And perhaps this is the lesson that winds quietly through all our wandering. Reality wears many masks, but for us, it is always lived. Matter may be mostly empty, time may be relative, consciousness may be emergent, and the universe may end in silence. But in the meantime, you are here, awake, experiencing the gift of a present moment. There is a soft humility in that. The universe is vast, mysterious, and perhaps stranger than we will ever know. Yet it does not withhold reality from you. Every breath, every heartbeat, every apple is an invitation to be present in the story. Whether we live in a block universe, a growing block, a hologram, or a mathematical structure, we live nonetheless. Think of your bed now, the fabric against your skin, the steady rhythm of your breathing, the way the world grows quieter as your eyes grow heavy. All of this is as real as it needs to be. Even if philosophers argue about simulations or panpsychism, the reality that matters is the one you feel, the comfort, the calm, the presence of rest. And maybe that is what being real truly means. Not permanence, not certainty, but immediacy. The apple you bite, the story you hear, the life you live. So as we close this exploration, let us circle back to the apple. Not sliced open into quarks and strings, not dissolved into bits of information, but whole, simple, nourishing. Reality may be physics, math, mind, or dream, but in the end you carry it with you in each small moment, in each act of noticing, in each breath, in each taste of sweetness. The questions will never be finished. Scientists will continue to chase deeper layers, philosophers will wrestle with doubt, and poets will try to capture the wonder. But tonight, you don't need all the answers. Tonight, you can rest in the knowledge that whatever reality is, it is enough. Enough to hold you, enough to soothe you, enough to be here with you as you drift into sleep. So close your eyes. Let the universe be as mysterious as it wishes. You are here, in your bed, with your breath, with your thoughts softening into dreams. The apple is real enough. The world is real enough. And your rest, in this moment, is as real as anything could be. Good night.